Hello children, welcome to Deeksha Online Classes. Today's topic Matrices and Determinants. We continue from lecture number 11. Lecture 11. So last classes we have seen the problems on the determinants and determinant applications and its properties. And today's lecture we start with the definition of inverse of the matrix and how to find the inverse of the matrix and certain examples. So first we see what is the inverse of the matrix. In other words, how do you find the inverse of the matrix? And is the matrix invertible? So first we start with the definition. If I consider a non-singular matrix of order n, and if there exists a matrix B such that AB is equals to BA is equals to I, AB equals to BA is equals to I, then the matrix A is said to be invertible. The matrix A is said to be invertible and B is called the inverse of the matrix A. It means for a non-singular matrix, if there exists a matrix B such that AB is equals to BA, that is equals to identity matrix, then A is said to be the A is said to be invertible and B is called the inverse of the matrix A. And we write down B is equals to A inverse. B is equals to A inverse. And now let us consider a theorem. If A is invertible matrix, then A inverse is equals to adjoint A by det A. A is invertible matrix, then I say that A inverse equals adjoint A by det A. How is it so? So A is invertible means that determinant of A is not equal to 0. So therefore A is invertible. A is invertible means nothing but A is non-singular. A is non-singular, which implies determinant of A is not equals to 0. And we know from the last lecture we had seen A into adjoint A is equals to det A multiplied by unit matrix. A into adjoint A is equals to det A into unit matrix. Clearly you see that since A is non-singular, det A not equal 0, that too this is a number. And this number, and if you divide by determinant of A, dividing by det A, we write down this one as A multiplied by adjoint A divided by det A is equals to unit matrix. In the same lines we can say that adjoint A divided by det A multiplied by A. Now this expression is in the form like A multiplied by B is equals to unit matrix, that is equals to B multiplied by A. Definitely by the definition of inverse of the matrix, the B matrix is nothing but the inverse of A. Therefore, I say that B is equals to A inverse. And therefore, from here, A inverse is nothing but B, which is adjoint A divided by det A. So, if A is invertible matrix, A is a non-singular and det A not equals 0 by the identity that A into adjoint A is equals to det A into I, dividing by determinant of A since it is not 0, A into adjoint A by det A is equals to I. That equals adjoint A by det A into A. So AB is equals to I, that is equals to BA, and this shows that the second matrix is the inverse of the first one. So A inverse is equals to adjoint A by det A, where det A not equals to 0. So therefore A inverse equals to adjoint A by det A. Now we shall see the property. First one, if A is a 2 by 2 matrix ABCD, where AD not equals to BC, the cross product is not equals to 0. AD minus BC not equals 0. Then A inverse equals to 1 by AD minus BC into D minus B minus A. Of course, this is same as adjoint A by det A, because we know the adjoint A is nothing but actually adjoint A by det A. That is nothing but A inverse. Det A for this one is nothing but actually AD minus BC. Multiply by adjoint. Adjoint is nothing but a transpose of the cofactors. A cofactor is equals to D, and therefore D will be getting B transpose. B cofactor is minus C, and of course transpose when you take up will be getting minus C here. And C cofactor is equals to B, keep it here, minus B, and A comes here. So therefore D minus B minus A. Remember the formula. This is for 2 by 2 matrix. For 2 by 2 matrix, inverse of the given matrix. Coming to the properties of inverse of the matrix. First one, A is non-singular, means determinant of A not equal 0, then A inverse exists. It means for the existence of A inverse, A is supposed to be, it is necessary that the matrix must be non-singular. Suppose if it is singular, A inverse does not exist. Directly we can say that. And the inverse of A inverse is equals to the matrix itself. A inverse whole inverse is equals to A. And the transpose of inverse matrix is nothing but a inverse transpose. Inverse of the transpose matrix. This is one more property. A inverse whole transpose equals to A transpose whole inverse. Why? Because you have the property that we know that A into A inverse is equals to unit matrix. If you take up the transpose of this one, both sides, A into A inverse whole transpose is equals to I transpose. That is A inverse transpose into A transpose is equals to unit matrix, and this is the inverse of this one. So A inverse whole transpose is nothing but A transpose whole inverse. Okay, right. Coming to continuation, next property. If A is a non-singular matrix, and if A is a symmetric, inverse is also symmetric matrix. If A is symmetric, then A inverse is also symmetric matrix. And if A is non-singular, det A not equals to 0, det of A inverse is equals to inverse of det A. Because when you take up A into A inverse is equals to unit matrix, take up determinant both sides, determinant of A into A inverse is equals to determinant of I. And that is det A multiplied by det of A inverse is equals to 1. Clearly you could see that the product is equals to 1 means none of this value 0, and I say determinant of A inverse is equals to 1 by det A. We know that det A is not equal to 0 because A, for the existence of A inverse, det A should not be 0. So that's the property. Det of A inverse is equals to inverse of det A. At the same time, if A and B are two invertible matrices of the same order, then AB is also invertible. That means AB whole inverse is equals to B inverse A inverse. This is the most important one. So we shall see the proof of this one. A comma B are invertible. So A comma B are invertible. So that implies A into A inverse is equals to I, that equals to A inverse into A. B into B inverse is equals to I, that is B inverse into B. Let me take up AB multiply by B inverse into A inverse. And that is equals to, using associativity, I say that this is nothing but AB multiply by B inverse, whole thing multiply by A inverse. That could be written as A into B inverse multiply by A inverse. We know B into B inverse is a unit matrix. So A into I into A inverse, that is equals to A inverse, because unit matrix into A itself is A. And A into A inverse is nothing but unit matrix. So AB matrix multiply B inverse A inverse is equals to unit matrix, you got it. The same way that you can take up B inverse A inverse into AB is equals to, it is B inverse of A inverse into A multiplied by B using associativity. That is B inverse into unit matrix into B is nothing but B itself. But B inverse into B is equals to unit matrix. So from this one, AB multiplied by B inverse into A inverse is I, and B inverse A inverse into AB is equals I. So AB multiplied by B inverse into A inverse is equals to B inverse A inverse multiplied by AB matrix is equals to unit matrix. And this is in the form of like xy is equals to yx is equals to unit matrix. Therefore, I say y is nothing but actually inverse of x inverse. That implies B inverse A inverse is same as AB whole inverse. So AB whole inverse is equals to B inverse A inverse. That is this property. And I is a unit matrix. Inverse of the unit matrix is the unit matrix itself. Coming to example on finding the inverse of the square matrix, given square matrix. If A matrix is given to you as 2, 1, 3, 4, minus 1, 0, minus 7, 2, how do you find inverse of this matrix? You know, inverse of the matrix is defined as adjoint A by det A. So it means A inverse is equals to adjoint A by det A. So calculate det A. To find inverse, first you calculate determinant of A and confirm whether it is singular or non-singular. If determinant is not 0, it is non-singular, inverse can be calculated. After that, adjoint A is nothing but actually transpose of the cofactors matrix. So we calculate in that way. First calculate determinant of A matrix. Determinant of A is equals to 2, 1, 3, 4, minus 1, 0, minus 7, 2, 1. So 2, 1, 3. 4 minus 1 0 minus 7 2 0, 7 to 1. the determinant value is equals to, it's 2 multiplied by minus 1 minus 1 multiplied by 4 minus 0, 4 plus 3 multiplied by, it's 8 minus 7, which is 1. And that is equals to minus 2 minus 4 plus 3. So this is minus 3. So determinant of A is minus 3. Clearly see that det A is not equals to 0. So that implies A is non-singular and it is invertible. A is non-singular and that implies A is invertible. Let us find out what you call the cofactors of elements of A. So the cofactors of elements of A is equals to, we'll be getting it like this. The cofactor of the first element is minus 1, 0, 2, 1. Second one cofactor is equals to, it's a 4, 0, minus 2, 1. Changing the sign of this one. Remember the signs as a positive, negative, positive, negative, positive, negative, positive, negative, positive. And the cofactor of the third element is, so 4 minus 2 minus 7, 2. Second row first column 1, 3, 2, 1 with minus sign change, cofactor. And second row second column 2, 3 minus 7, 1, 2, 3 minus 7, 1. And the next one cofactor of the element 0, it's 2, 1 minus 7, 2. 2, 1 minus 7, 2, change the sign. And minus 7 cofactor 1, 3 minus 1, 0. 1, 3 minus 1, 0. Next, minus of 2, 3, 4, 0. And lastly, which is 2, 1, 4 minus 1. 2, 1, 4 minus 1. And the evaluation of these gives us a matrix like this. Minus 1 minus 0, so minus 1. And you'll be getting minus 4. 8 minus 7, 1. 1 minus 6. Minus 5 minus half minus plus 2 plus 3 10 2 21 sorry, so 2 plus 21 23, 4 plus 7 11 minus of 11, 0 minus 3 minus of minus plus 3, 0 plus 12 and minus 6. This about cofactors matrix. While calculating the adjoint, you have to take the transpose of this one. So adjoint matrix is equals to, so adjoint of the matrix divided by det A. So you calculate the adjoint of this matrix. Adjoint A is equals to the transpose of cofactors matrix. Cofactors matrix. So the adjoint transpose of the adjoint cofactors matrix is nothing but adjoint of the matrix. Now inverse is nothing but adjoint A by det A. So therefore A inverse is equals to adjoint A by det A. Therefore determinant of A is equals to minus 3. So minus 1 by 3 multiplied by the transpose of the cofactors matrix minus 1. So column wise let me take up minus 1 5 3. Here you write down row wise 5 3. And column wise minus 4 23 12. Minus 4 23 12. Of course it is 3. And 1 minus 11 minus 6. 1 minus 11 minus 6. This is the inverse of the given matrix. So let's see that. So minus 1 by 3, minus 1, 5, 3, correct. Minus 4, 23, 12, correct. 1 minus 11, minus 6. So the answer is this one. This is how we calculate the inverse of the matrix. Hope is it clear to you? Let's proceed to the second example. You are given A comma B 2 by 2 matrices. You are asked to verify AB whole inverse is equals to B inverse A inverse. We know how to find the inverse of a 2 by 2 matrix by a formula that. So AB, I'll write here. So if A is equals to ABCD, then inverse of this matrix is 1 by AD minus BC times of D minus B minus C A. This is the formula. Let's take up A is equals to 2, 3 minus 4. A is equals to 2, 3 minus 4, 1 minus 4. And B matrix is equals to 1 minus 2 minus 1, 3. 1 minus 2 minus 1, 3. Let me calculate A inverse 1 by AD minus BC. So which is minus 8 minus 3. The product of these two minus the product of these two. So minus 8 minus 3 multiply by D minus B minus C A. D means this number minus 4 minus B minus 3 minus C minus 1 A which is equals to 2. And which is nothing but minus 1 by 11 times minus 4 minus 3 minus 1 and 2. Let me calculate in the same way B inverse 1 by AD minus BC which is 2. D, I think 3 comes here, and minus B plus 2 minus C plus 1 and A it is 1. And that gives you the inverse 3, 2, 1, 1. B inverse. Let me calculate a B matrix which is the product 2, 3, 1 minus 4 multiply by 1 minus 2 minus 1, 3. And the product of these two. So that is equals to the matrix here. So the product is equals to first row, first column 2 minus 3, 1 plus 2 plus 2 minus 3 plus 2 minus 3 minus 1 minus 4 plus 9 5 1 plus 4 5 and minus 2 minus 12 minus 14. And the inverse of this matrix can be calculated. AB whole inverse can be written as, and that is equals to 1 by AD minus BC 14 minus 25 times D minus 14 minus B minus 5 minus C minus 5 and A minus 1. 14 that is equals to minus 1 by 11 times of minus 14 minus 5 minus 5 and minus 1. Okay, let us keep this AB whole inverse and let me calculate what is B inverse A inverse. So B inverse into A inverse is equals to, so the B inverse is equals to 3, 2, 1, 1. So you got a 3, 2, 1, 1 multiply by 1. A inverse is minus 1 by 11 times of minus 4 minus 3 minus 1, 2 minus 1, 2. The product is equals to 1 by 11 times of the product. When you take up the product of first row, first column, minus 12 minus 2 minus 14. Yes, minus 14. However, it is minus 11, 1 by 11 into minus 14. And minus 9 minus plus 4 plus 5. So minus 9 plus 4 minus 5. And the next one, minus 4 minus 1 minus 5. And minus 3 plus 2. It is minus 1. And of course, this is minus 14 minus 5 minus 5 minus 1. Clearly, you could see that that is nothing but AB whole inverse. And that is AB whole inverse. So minus 1 by 11 minus 14 minus 5 and minus 5 minus 1. Yes, same as it is. So therefore, we got AB taken whole inverse is equals to B inverse A inverse. So we have proved the concept in this one. AB whole inverse is equals to B inverse into A inverse. Okay, verification of the theorem. Now, another example, which is for a matrix A is equals to 1, 1, 1, 1, 2, minus 3, 2, minus 1, 3, show that the identity A cube minus 6A square plus 5A plus 11I3 is equal to 0. Hence find A inverse. Hence find A inverse, the matrix. A matrix is given to you, and first we have to prove the identity, show that. Then we have to find inverse. Let me work out here. A matrix is given to you, so I'll write here A is equals to, the matrix is given to you, 1, 1, 1, 1, 2 minus 3, 1, 1, 1, 1, 2 minus 3, 2 minus 1, 3, 2 minus 1, 3. This is the matrix. Let me evaluate A cube, which is nothing but A square, A into A. So it is A multiplied by A square. So A multiplied by 1, 1, 1, 1, 2 minus 3 and 2 minus 1, 3. Multiply by 1, 1, 1, 1, 2 minus 3, 2 minus 1, 3. The product. And that is equals to, given by the product. And that is given by A multiplied by the matrix here. So you have, so 1 plus 1 plus 2. I hope you'll be getting 4. And 1 plus 2, 1. First row, first column. First row, second column. 1 plus 2, 3 minus 1. It is 2. And 1 minus 3 plus 3 gives us 1 here. Next, second row, first column. 1 plus 2, 3 minus 6 minus 3. And second row, second column, 1 plus 4, 5 plus 3, 8. And first row, third column, 1 minus 6 minus 5 minus 9, minus 14. Third row, first column, 2 minus 1, 1 plus 6, it is 7. And the third row, second column, 2 minus 2, 0 minus 3. And 2 plus 3, 5 plus 9, 14. And let me take up the product of this again now. That is equals to 1, 1, 1. It's 1, 1, 1. 1, 2 minus 3. 2 minus 1, 3 multiply by. It's 4, 2, 1 minus 3, 8 minus 14. Okay, 7 minus 3, 14. The product of these two is equals to, it gives you 4 minus 3, 1 plus 7. I hope you'll be getting 8. Next, 2 plus 8, 10 minus 3, 7. 1 minus 14, minus 13 plus 14, 1. Next, so 1 I think 4 minus 6 minus 2 minus 21 minus 23 and 2 plus 16, 18 plus 9, 27. It's a 1 minus 14. So 1 minus 28. So 1 minus 28, 27 minus 42 minus, so 1 minus 28 minus 42. So this is, I think, 60, 70, 69 minus 69. Next, you'll be getting 8 plus 3 plus 21. So 11, 32. And the next one, I hope you'll be getting 4 minus 8 minus 9. So you have a minus 13 and plus 2 plus 14 and plus 42. 42 means 56, 58. This is 58. This you got a cube. Now I have to get it. A cube minus 6a square plus 5a plus 11i. I have to calculate a cube minus 6a square plus 5a plus 11i. We need to simplify this value. A cube minus 6a square plus 5a plus 11 times unit matrix is equals to, a cube is this matrix. I hope you'll be getting 8, 7, 1, minus 23, 27, minus 69, 32, minus 13, 58. Minus 6 times of a square. A into a square, you got a square here. This is a square matrix. Multiply by 6. Okay, it is 6 4s, 24, 6 12s, 6 1s, 6 3s, 18, 6 8s, 48, and 6 14s, minus 84, 6 7s, 42, and 6 3s, minus 18 and 84. And plus 5 times of A. So 5 times of A matrix. A matrix is equals to 5, 5, 5, 5, 10, minus 15, and 10, minus 5, 15. Of course, plus 11 times of unit matrix. That will take up that later. That is equals to. So first let me simplify only this particular part of this value. Okay, a cube minus 6a square plus 5a value. That is equals to. Clearly you can see that 8 plus 5, 13 minus this value. 13. 13 when you subtract, you'll be getting minus 11. So that gives you the value that is equals to minus 11. Second element is 7 plus 5, 12 minus 12, 0. Third element 1 minus 5. Yes, 1 plus 5, 6 plus 6 is 0. Minus 23 plus 23, 0. 27, of course, 69 plus 15. So this is a 0. Next, minus 23 plus 18 plus 5. 23, 23. This is 0. 27 and plus 10. 37 when you subtract, you'll be getting 11 minus 11. 69 and 15, 84. Of course, this is a 0. Similar way, you'll be getting 0, 0 minus 11. And that is equals to 11 times of unit matrix. You got it. So you got a cube minus 6a square. A cube minus 6a square plus 5a is equals to 11i. Sorry, minus 11 times of I. Bring it left hand side, you'll be getting plus 11 times of I is equal to 0. We got the condition. And then you require to find the inverse of this, inverse of this matrix. From hence find inverse means from this condition you have to get it A inverse. How do I get A inverse from this one? Let us see. As this identity we got it, why not you multiply A inverse both sides? To find A inverse, let me multiply A inverse both sides, which is A cube minus 6A square plus 5 times of A plus 11I is equals to A inverse into null matrix. That implies, we know by the property that A inverse, we know the property A inverse into A is equals to unit matrix. By using this one A inverse A is identity. Identity multiplied by A square will become A square. Minus 6 multiplied by A inverse into A square will be getting A. 5 times of A inverse into A is a unit matrix plus 11 multiplied by A inverse. That is equals to null matrix multiplied by A inverse is a null matrix. From here, I can find out inverse of the matrix. So 11 times of A inverse is nothing but, so which is minus of A square minus 6A plus 5 times of unit matrix. We had already these values of A square and this particular numbers, and you can substitute and you can calculate, divide by 11. Lastly, you'll be getting the required answer. So therefore, 11 times of A inverse is equals to A inverse is equals to minus 1 by 11 times A square minus 6A plus 5 times I. So let me calculate A square minus 6A plus 5 times I is equals to. So A square, you know the matrix is equals to, A square equals to 4, 2 minus 1. So 4, 2 minus 1. Minus 3, 8 minus 14. Minus 3, 8 minus 14. 7 minus 3, 14. 7 minus 3, 14. This is A square matrix. Minus 6 times A. A equals to 1, 1, 1. Means multiply by 6 times of 1, 1, 1. 1, 2 minus 3. 1, 2 minus 3. And 2 minus 1, 3. 2 minus 1, 3. Plus 5 times unit matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Let me simplify this one. You will be getting 4, 2, minus 1. Yeah, of course, you can directly calculate minus 3, 8 minus 14. 7 minus 3, 14. Minus 6, 6, 6. 6, 12 minus 6. And it is 12 minus 6 and 18 plus 500, 050, When you simplify, clearly you can see that 4 plus 5, 9 minus 6. You got minus 3, and that gives you the value is equals to, plus 3. Yes, and 2 minus 6 minus 4. Minus 1 minus 6 minus 7. Minus 1 and minus 6. Is it minus 1? 4 to 1. Yeah. It's a plus 1, plus 1. Yeah, 1 minus 5. Minus 3 plus 6 plus 3. Minus 3 minus 3, 9, sorry. Which is minus 9. And 8 minus 12 minus 8 minus 12 minus 4 plus 5 plus 1. Minus 14 plus 6. I think it is 8. 14 minus 6. Let me check. Yeah, minus 14. 6 3s are 18, I think so. Yes, 18 this one. Minus 14 plus 18. you have plus 4, and 7 minus you have minus 5, 7 minus 12, minus 3 plus 6, it is plus 3, 7 minus 18, no sorry, 14, 14 minus 18, minus 4 plus 5 plus 1. And therefore, now we can take up A inverse is equals to minus 1 by 11 times of this one. So therefore, minus 1 by 11 times of this matrix. 3 minus 4 minus 5, minus 9, 1, 4, minus 5, 3 and 1. Of course, that 1 by 11 times of minus 3, 4, 5, 9 minus 1 minus 4, and 5 minus 3 minus 1. So clearly see that minus 3, 4, 5, yes, 9 minus 1 minus 4, and 5 minus 3 minus 1. Clear? The answer is correct. So we need the patience to calculate very carefully. So evaluate with the ease in calculations, you will be getting answer. Hope you understood. So first you have to calculate a cube, then simplify this a square value also. You can use it from here and you can simplify and get the relation here, and then multiply A inverse both sides. You will be getting one condition here. From this condition, evaluate A inverse is a methodology. Coming to the next example, let A be a non-singular matrix of order 3 by 3. A is a non-singular matrix of order 3 by 3. Det A is equals to 4. Then determinant of adjoint A is equals to det A power n minus 1. A is a non-singular matrix of order 3 by 3. Det A is equals to 4. Det of adjoint A. I hope it's very simple. So 16. Hope it is very simple. So we can see that det of adjoint A, we know by the basic property, det of adjoint A is det A to the power of n minus 1. If A is a matrix of order 3 by 3, n is equals to 3. That is det A to the power of 3 minus 1 det A whole square. But you are given det A is equals to plus 4. So that is a 4 square, that is equals to 16. That is 16 is the answer. So these are the points which we learned today. We had inverse of the matrix based on the determinants and its properties. Okay. So work out the examples in the manual and then get back by completion of the homework. I conclude this lesson. Now we continue the next lecture in the next video. Thank you.